Thursday this week, probably around about a half hour or so after class. Dave Messenger is going to come in to class and present all the projects that we have in remote sensing as far as master's and PhD theses go. So what we're going to ask you to do after that, if you're interested in working with anybody in the remote sensing group, is to rank the projects that you see as, you know, this is the one I'd like to do most, this is the one I'd like to do second most, this is the one I'd like to do third most. So we ask you to pick your top 3 choices, and then we'll get together over the next couple of weeks and we'll try and divide projects up and make sure everybody has something who does want something in remote sensing. Right? So, like I said, I think he'll take about a half hour out of class next time to go over all those things. I think there's a bunch of projects, so there should be plenty to pick from. All right. Any questions about anything to this point? All right. So what I'm going to do is I'm going to go over one more supervised classification technique called spectral angle mapper, which has some distinct advantages and some problems associated with it. It's a fairly popular alternative to something simple like minimum distance to the mean, and it exhibits, you know, very fast speed, very similar to minimum distance to mean because the computation's quick. But it does have an advantage, and the advantage is that I think I mentioned, might have been last time, that when we're picking training samples, we have this tendency to pick them because of their cultural significance rather than their statistical dissimilarity from other classes, right? And that's a natural thing when we look at scenes. But one of the things that we'll do very often is we'll identify, let's say, let's select grass as a land cover type. We might identify grass in the scene, and we might pick a region of interest. And then we might identify grass again somewhere else, and grass somewhere else in the scene. We might pick 3 or 4 different samples, and thinking we're getting a really nice, robust statistical description of what grass looks like. And in doing that, we might make a couple mistakes. One of them, we might pick different grass types that have very different spectral signatures. So that could result in a larger than normal class as far as the statistical distribution goes. And that's problematic, and that's one that you need to try to avoid. And how do you do that? Well, while you're picking those samples, look at the spectral signatures, right? And we'll let you look, and most packages will let you look at spectral signatures as you're picking certain collections of pixels. And if they look dramatically different than the last one you picked, it's probably a different class, and you should probably call it a different class. Now, another problem comes into play when you have the same land cover type. So let's say we have a nice, beautiful front lawn somewhere. Well, it's all Kentucky bluegrass, right? So it is a single particular species of grass. And we draw a region of interest, and part of that region of interest is in the sunlight and part of it's in the shade, right? So let's say we're working on imagery at a resolution where we can actually see shadows, right? So obviously not Landsat, let's say we have aircraft. Or if you're looking at something of Landsat imagery, and let's say you're looking at an area where you have mountains, on one side of a mountain it might be sunlit, on the other side of the mountain it might be shaded, but there might be the same land cover type on both sides, right? So what happens there? The spectral signature is the same because the material is the same, right? But the overall level of the radiance that's reaching the front end of the sensor will vary in magnitude, right? So you could have two spectral signatures that are shaped identically. Fresh program. So if we were looking at grass, and what we're looking at here is a reflected signature. So that's well, that's the reflected signature. There's no question about that. That's what it's always going to look like because the material hasn't changed. Right? But if we now overplot on here radiance, plot radiance, let's ignore the shape of the source response function, or the source energy function for now. And let me just draw a curve that looks similar to this. We may get a radiance value that looks like this, and so let's say we have a spectrally flat source, and we get a nice curve out. No atmospheric effects, no upwell gradients, none of that. All right, so this is just a perfectly clear atmosphere, perfectly flat spectral distribution for our source. You might get a radiance curve out that looks like this. But you also might get one out that looks like this. So the same shape, but much lower magnitude. Okay, so this one might indicate grass that's in a shadow, and this might indicate grass that's in the sun. Okay. Right, when that's radiance.
The shape that you draw in the peaks, is that intended, or is this?
No, it's sloppy. Yeah, the peaks should all line up with one another. Yeah, I started shifting a little bit here, and I shifted even more once I got over there. Yeah, those all line up. Okay.
So if you normalize all the curves, then you should be able to tell that they're really the same thing.
If you normalize them by what?
By the peak.
So if you were to say normalize, by the magnitude, let's see, divide by that peak, and you should get a peak of 1.
Mm-hmm.
Divide by this peak, you should get a peak of 1, and then they should fall on top of 1.
Mm-hmm.
Sure, absolutely. And that's what this technique sort of attempts to do. All right, so if we think about, let's pick a couple points here. Let's pick those 2 points and these 2 points. These peaks right here, those 2 points. All right, now if I were to go ahead and take that 3-band system, right? I pick three points on each curve, so that's equivalent of 3 bands that we might be looking at. And if I were to plot in 3 space those points, right? How would they look? How would they arrange themselves relative?
What are your axes?
Band 1, band 2, band 3.
Would band 1
3
and 3
band.
be, would they be orthogonal to each other?
Would 1, 2, and 3 be? I mean, we're just plotting them in Cartesian space, in digital count space. Right, so this is just digital count band 3, digital count band 2, and digital count band. All right, so let's just say 1 point plots right here. Right, and that's this point, that point. So the vector formed by the 3 bands on the sunlit curve. Let's say it plots there. Now that's just a point in 3 space, right? It's a vector x, has 3 elements in it, just plots at a point in 3 space. And if I drew a vector from the origin, to that point, it would reach that point in 3 space. And I could project that down onto a plane, and it might project out at that point right there. Now, if I took the pixel value, right, the 3 vector for the shadow curve, where would that fall?
It would just be on that same vector.
Yeah. Right, so it would fall right on that same vector, but the vector would be shorter. Okay? It would be in the same direction, and the direction is given by the color. Right? In this case, I'm calling it a color. It's 3 bands, but it could be 100 bands. It's the color, right? And the length of that vector is going to be related to the relative magnitude of the curve. Right? So going back to what you said, Maria, if you normalize them, that would be a normal vector. If you normalize the vector, and then they'd be identical.
But you can just compare the angle between the two and hope to be identical.
That's hence the name of the technique, the spectral angle mapper. All right. All right. So if we look at the way this works, this technique's called spectral angle mapper. Last time I mentioned, I showed you a tool called. Wow, totally lost what the tool was called. The thing we looked at where we plotted the n-dimensional visualizer. All right. And mentioned that Joe Boardman, one of the co-authors of Envy, had done that as his dissertation. This was another paper that Joe put out a couple of years after the fact on how to do classification that is robust to illumination factors. And he named that technique spectral angle mapper. All right, so let's say we have two points in space, as drawn here. I have a point B and a point A, right? They both are a vector originating at the origin. And if I wanted to compute the angle between those two vectors, what would I do? Well, I'd take the dot product of those two vectors and divide it by the product of the magnitudes, right? That would give me the cosine of the angle between the two vectors. And then I could take the arc cosine and get the angle theta. Right? So that equation right there is the angle between two vectors. Right? So that's nothing new. You've done that before. All right. So how do you use that as a classifier? Well, if two identical classes always point in the same direction, right? If I have a class of grass and it's sunlit, and a class of grass and it's shaded, it's the same land cover type. They point in the same direction, so they might have different magnitudes, but the angle between them is going to be 0. Right? If I have two different classes, like you might see right here, A and B, they point in different directions. And the angle between those two vectors, theta, is something greater than 0. Now, this angle between two vectors concept works in n dimensions, right? It just depends on the number of elements in your vectors. So if you have a hyperspectral data set with 100 or so bands in there, you would just have a dot product between two vectors that have 100 or so bands. And what you come out with is a scalar divided by a scalar, which is the cosine, and you get your angle in n space. Okay? But the same concept holds true. The angle between those vectors, if the classes are identical, would be 0. So to turn this into a classifier, it's just like minimum distance to mean. Minimum distance to mean said, which mean am I closest to? Spectral angle mapper says, which mean do I have the smallest angle compared to? All right, so if I were to pick all my training samples, compute the mean vector, each of those mean vectors would be a vector in space, in n space. I take my unknown pixel, plot it as a vector in n space, and compute the angle to all the means. So it is a minimum distance to the mean sort of classifier, only the distance measured here is angular. So really simple concept. There's an example if you haven't computed before. And what is our decision rule, our discriminant function in this case? Well, that vector x is going to be an element of omega I, just like we've said in the past, if the angle formed between x and the mean of I is less than, not greater than. That's a mistake. Less than all the other angles, right? Because you want the smallest angle. All right, so this just looks at the spectral nature of the curve. It doesn't care about the relative magnitude of that curve. Right? All the other classifiers that we've looked at so far, maximum likelihood, Mahler-Novis distance, minimum distance to the mean, that magnitude would have made a difference. If the pixel was brighter, its mean would be further away. Then if I tried to put a shadowed pixel and I use minimum distance to mean, I get a very large Euclidean distance because of that magnitude. This is the only one that incorporates. All right, now, I want to try and justify why I put a greater than sign there. If you're actually doing this for real, and you go back and you look at the equation here, there is never a reason to actually compute the arc cosine, because the cosine of the angle, the dot product over the product of the magnitudes, is going to be greatest for the one it's closest to. Right, because cosine of 1 is 0. Right, 0 degrees has a cosine of 1. Right, so cosine for an angle of 0 would be the largest they could possibly have. So if I wanted this decision rule to read correctly, I could say the cosine of theta sub I is greater than the cosine of theta sub j for all j not equal to I. Cosine's an expensive function to compute, so why compute it? Right, if you're writing code, you want it to go fast, you just leave it as that dot product over the product of magnitudes. All right. So, everybody's good with that? All right. So now let's take a little bit of a look at how we actually can take into account some of the things that we may want to, as opposed to in regards to how important a particular class is with reference to another class. Right. So up till now, we've been treating all classes the same. Right. We've been saying I have grass and I have forest and I have urban features. And I want to go ahead and I want to classify those, and I want to do a good job on everything. Right? That's, I don't know, that's probably what you do most of the time. If what you're trying to make is a thematic map, if what you're trying to make is a map of the area, and you're trying to label land cover types, and you want it to be accurate, you probably want to be do as well as you can. Right? But there might be situations where certain classes are more important than other classes in your scene. Right, so if I want to map out roadways, and I want to have a really good map of the roadway infrastructure from a Landsat scene, do I care if I get maple trees mixed up with elm trees, mixed up with ash trees, and the extent of my botany there? There's probably maple trees. Sorry, maple trees. If I don't want to. If I don't care about mixing those up, and probably if I'm trying to map roadways out, I probably don't care about that. Okay? Can I make my classifier do a better job on some classes than on others? Right? I think John in his book, if I remember correctly, refers to identifying areas that have maybe toxic leaks from waste dumps, and you want to identify the toxic waste as opposed to really caring about soil type, right? Because you don't want to miss somewhere in your scene where there might be a spill that you want to clean up because you really want to get the maple trees correct, right? There may be times when you want to get the maple trees correctly and you're willing to let something else go a little bit. And when you look at these things, at least in two-space, we talked about this when we first started looking at distributions, but we're always going to make mistakes, right? We're always going to have two overlapping probability distribution functions. Here's 3 shown for class 1, class 2, and class 3. Right? So given the digital count, what's probability of being in class 1, class 2, and class 3? Right? So these are the normal distributions. These are the the Mahalanobis distance based distribution in n space. Right? And these distributions overlap one another. Right? In 2 space, it's easy to see that overlap. In 3 space, you can imagine what it looks like. But there's 2 mistakes that you can make here. Right? There's this mistake where the class 2 distribution falls over and overlaps the class 1 distribution. So there's pixels on this side of the decision boundary, right, that are actually in class 2, but they're going to be classified as class 1. Right? And there's pixels on this side of the decision boundary that are pixels that are in class 1 that would be classified in class 2. So the way we normally refer to this is, let's see, what's this in regards to? This is in regards to class 1. All right, so if I'm interested in pixels in class 1, these targets that fall on the other side of this decision boundary and are classified as class 2 are going to be errors that I missed, or errors due to missed targets. So I'm going to miss these. Ones that fall on this side, if target 1 is what I'm interested in, and I identify some pixels that were in class 2 as pixels that were in class 1, we're going to call those false alarms. Okay. So those are the two mistakes that I could possibly make. The one on the left-hand side here is what's called an error of commission. I don't know if you remember that from your probability class. And the ones that fall on the right-hand side, with regards to class 1, are the errors of omission. And so you'll probably, if you look back at your stats book, you probably remember reading that at one point. Errors of commission are false alarms, error of omission are missed targets. Now, if class 1 is really important, right, if class 1, let's go back to let's map the roadways example. If I want to make sure I get all the roadways, I don't want to have any missed targets. Right? So what would I do? Well, I would take this decision boundary and just push it over to the right. Now, that gives me more false alarms, but it gives me fewer missed targets. Right? So you have to weigh that and say what's more important to you. Making sure you get all the type 1 pixels, and you're willing to live with more false alarms, or is some other rule what's going to be important to you. All right, so in order to push that one way or the other, it's easy to do here in 2-space, right? You can imagine just pushing that line one way or the other, and you're just basing it on the digital count. But in order to do that in n-space, what you're going to want to do is come up with a function that are called risk or loss functions that you can go ahead and you can modify those decision boundaries with them. All right, so what's a risk function? Well, it looks like this, where this again is either the Gaussian normal or the multivariate normal probability density function for class J given the digital count. That's your normal distribution for, given the training statistics that you have to be in the covariance matrix. This function here, L of ij, is what's called your loss function. And in this particular case, the way this is written, that given class J, right, given that my pixel is in class J, what loss will I incur, or how serious will the error be if I place it in class I? So these are sort of, you can assign these in many ways. I mean, they could be fractional values between 0 and 1, where 1 would say the loss is, having a loss of saying it's I when it really was J is really big. You can assign that loss function a value close to 1. And when the loss is very small, if I assign a pixel to class I, given that it's really in class J, I can assign a loss value of 0. And what that'll do, once I sum those up over all classes in my scene, so what am I going to do? Well, I'm going to look at all the other classes, J, and figure out what that loss function is for each of those classes, and go in and multiply by the probabilities, sum those all up. That'll give me a risk factor for that particular digital count when I'm trying to assign something to class I. All right, now, so you can assign these as just scalar values between 0 and 1 to each of those possible mistakes that you can make. Or if what you were looking at, well, let's say you were looking at the yield of a wheat crop, for instance, and you were really concerned that you get the amount of wheat in the scene correct, because you were going to go out and harvest and bring that wheat to market. You wanted to make sure you had you were harvesting the right wheat, right? That you're going out in the right week to get the maximum yield out of that field. Well, it would be very important that you identified all the pixels in that scene of wheat so you got an accurate inventory. So you can actually assign a loss function here based on cost, right? I mean, you could put a dollar amount there. It's just a number, right? That number can mean anything, but if something is very important monetarily, you could give it a high cost value, right? Meaning that the error would be very costly to you. Right? It would be high risk. Right? It's just like assigning it a value of 1 in the previous example. So what you wind up with for this loss function right here is you usually identify what's called a loss or a cost matrix. Now, I think the terminology here is a little weird, but if you look at it closely, I think it starts to make a little bit of sense. So what do we have? We have a matrix here with class 1, 2, and 3 across the top, class 1, 2, and 3 down the side. Okay? And each entry here, this is the L of I given J entry, is going to be the loss function that we use in this previous equation. All right, so let's take a look at the two cases that were in the text. So case 1, you have a high cost of false alarms. All right, so that means if I include pixels in my class that are really false alarms, right? They really belong to class 2, but I included them in class 1. Right? If that has a high cost, my cost matrix might look something like this. Right? So I have a high cost of false alarms, and the assigned, and what end is assigned to class is? All right, so if I assign to the class across the top here, when the pixel is actually in the class down the side here. All right, so what does that mean? If I actually assign a pixel to class 2, and it's really in class 1, what is my loss factor? Well, it's this factor right here, 0.5. All right, so what does that say? Well, it says that that's less important to me. Okay, it's a number lower than 1. It's less important to me than if I assigned a pixel to class 1 when it was really in class 2. That's more important. Okay? So this is how you would reduce a false alarm. So if you were in a military scenario and you were trying to pick out targets, right? And you know, I was going to place a munition on target, I want to make sure I don't have false alarms. Right? So in that case, I might set up a matrix. You know, it looks like this. Now, let's look at the other one. So this would be the minimizing the cost associated with an error of commission, right? Falling to the left-hand side of that decision point when you're interested in class 1. All right, case 2, high cost of missing the primary target. All right, so what does that mean? Well, that's on the other side of that curve. That's the missed target side. All right, so in that same case, if I was more worried about missing targets that fell to the right of that decision point, I'd want to push that decision boundary off to the right-hand side. Right? So in that case, I would reverse these two values, and I would place a higher cost on assigning a pixel to class 2 when it was really in class 1. Right? And I'd assign a lesser cost to assigning a pixel to class 1 when it was really in class 2. Okay? So what they wind up doing, to go back to this equation for a second, is it's just a modifier on your probability. Right? It's just a multiplier on the probability term, which reduces its effect. So it shifts that curve one way or the other. Or I'm sorry, that decision point. This line right here will shift it one way or the other because it will reduce or increase the height of that curve. Does that make sense? You're going to say something. You're like
I'm just trying to process.
To be totally honest with you, I've never done this. Right? In reality, I've never assigned cost functions. I've always tried to get, you know, the best accuracy everywhere that I can get whenever I've done classification. I could definitely see where this would be very valuable. If you look in a lot of the software that's out there, AirDOS and Envy in particular, there is no way to implement this directly, right, in their software. So you'd have to write some code offline to actually do this. It's not that it's hard code to write; it's easy code to write, but you would have to do it offline because I haven't seen it. But it is a very valuable thing if you do want to wind up shifting those curves. But you've got to be very careful in selecting these values. because these are going to have a big effect on your classification accuracy. All right, so if I apply a loss function of any sort, and I change my decision boundaries, what's going to happen to my overall classification accuracy, let's see? It's going to change. It should get worse, right? I mean, the whole idea of Gaussian maximum likelihood and minimum distance to the mean is that it does place these boundaries at the point where you should get the best classification accuracy that you can, right? So moving this one way or the other is going to change that accuracy, and it's going to change it for the worse. Right? So you know, just got to be aware that if overall classification accuracy is what you're going for, then doing something like this could affect that. But if going for particularly high classification accuracy for a particular class is very important to you, right? If we go back to that image that we pulled up the other day when we were looking at textures, and we had the cornfield and there was the marijuana plot in the middle, right? The cost of misidentifying the marijuana stand is probably higher than this cost by the corn, in a commodity sense, right? Okay, so how do we? So on that note, how do we actually assess accuracy of classification? Yes. Let me blast ahead here a little bit. All right. So there is a concept that's been around forever, and it's in all the stats books on classification techniques and multivariate analyses. It's been in the world sensing literature forever, and it's the de facto standard of how you identify classification accuracy. But it is the one single tool that allows you to lie with statistics the best I could ever see. All right, so you can make yourself look really good with this tool, or you can be very honest with this tool. And I want to show you the whole gamut. Right? Because I really want you to understand that when you're looking at a paper, you're reading somebody's results, and they said, well, we applied a Gaussian maximum likelihood classifier, we achieved the classification accuracy at 97.3%, and you know, we have the greatest algorithm in the world, the greatest sensor in the world. That may be very true, right? But I want you to read those papers very carefully and understand how they're reporting their accuracies, and see if they're just trying to overinflate what they're doing. Okay, so let's talk about the concept of a confusion matrix, or what's called a contingency table. You'll see both names, and you know, let's take a look at how they're composed. All right, so across the top we've labeled different classes, right? So here they're just labeled class 1, class 2, class 3, class 4, and class 5, but that could be deciduous trees, coniferous trees, grass, water, and concrete. So just labels for your classes across the top, labels for your classes down the side. All right. Each element in this matrix is going to indicate either a number of pixels or a percentage of total pixels. Right? And you'll see these tables formed both ways that happen to fall in a particular bin as far as classification went. All right. So now, not always, but I would say 90% of the time, these tables are laid out as follows. The rows in the table represent the actual true class that a pixel belongs to, right? And the columns of the table represent the classes that a classifier assigned a pixel to, right? So a pixel really belongs to a particular class, but a classifier can assign it to any one of the 5 classes in this case. Right? If it assigns it to any one except the right one, that's a mistake. So across the top is what the classifier assigns it to, and down the side is the ground truth, right? What the pixel actually belongs to. All right, so how do we read this? Well, the classifier assigned 99.3% of the pixels that are in class 1 to class 1. It assigned 7/10 of the pixels to class 3, that really are class 1. Okay? So the rows of this matrix, if you were to produce marginals on the side here, the rows will always add up to 100%. Because this is the truth in the row. All right, so here in the second row, 12.8% of the pixels were assigned to class 3 when they were really in class 2. And that's how the whole matrix is laid out. Now, it's non-symmetric, right? Because assigning a pixel to class 3 when it was really in class 1 is not the same as assigning a pixel to class 1 when it was really in class 3. Those are different errors. So it's non-symmetric, so you need to go ahead and you need to compute every cell here. Your hope is that you get 100% down the major diagonal, right? Pixels are assigned to class 1 that are in class 1. Pixels assigned to class 2 are in class 2, and so on. So you'd like to see 100% down that major diagonal. All right, that makes sense? All right, now if I said, how good is the classifier? And you look at this table, well, there's a lot of things you might think of doing. What can you think of doing?
Give you the average or the lowest
What's that?
of the diagonal. So you could say it's only as good as 80, but then you could also average it to make it look a lot higher.
Yep. You can say, hey, the worst I did was 80%. The best I did was 100%. The average of what I did, you can take those diagonal elements and average those. You can do any of those statistics. That's a little deceptive, right? Let's say this 100% was based on 7 pixels, and this 80% was based on 3,000 pixels, right? That could be very deceptive, a straight average. So you might do a weighted average. Right? Weight it by the number of pixels compared to the total number of pixels, and do a weighted average of the major diagonal. Right? So people will report a weighted average. People will report a straight average. People will report minimums. People will report maximums. You'll see all those kind of things reported. All right, and that's pretty easy to figure out. All right, it's easy to understand that. You can then say, okay, well, hey, they reported a straight average, but there was only a couple of those pixels. That's not really a good estimate. You should be critical of how they report that. All right, now here's the other thing that you can do. There's 3 confusion matrices labeled here. One's labeled dependent data, independent data, and randomly selected data. All right, what does that mean? Dependent data. A lot of times people will take their training regions of interest, right, the ROIs that they made, that they developed their statistics on it, that they developed the classifier and discriminant functions on it, run those pixels through the classifier and see how they get classified. Right? So what did you just do? Well, you took the data that you trained with and you evaluated how well you can do on that same set of data. Right? There's nothing wrong with that per se, but it's not very robust. Right? If your intent was to pick a region of interest that represented all the trees in the scene, and all you evaluated on was the particular tree that you selected, well, you might identify that tree very well, but when you look at the rest of the trees in the scene, you might do a very terrible job. Right? So this is probably the worst case. All right? And if you're seeing classification accuracies and they say they did it on a dependent data set or on their training data, you know, if you look at the words that they use to describe how they selected it, this is probably the most overestimated classification accuracy that you get. All right, now, this is a good one, independent data set. What does that mean? It says, choose another set of ROIs to do this analysis with. Right? So choose a set of regions of interest to train your classification algorithm. Pick trees, pick concrete, pick grass, come up with the statistics, develop your classifier, classify your scene. Right, now when you want to evaluate how well you did, go in and select a whole different set of regions of interest for those same classes and use those to develop your confusion matrix. All right, so now you're using data that was not used in the training at all, and will do probably a better estimate. Almost certainly it'll give you lower accuracy. In the example here, you can see that everything dropped by several percent. In some case here, that one's 12%, 74 and 86. Right? And you'll see drops like that because you're not using the same data that you trained with. All right, now, that's That's a little bit more work though, right? If you went in and you selected regions of interest to develop your classifier, now you got to go in and you got to select more regions of interest to evaluate it. And I don't know if you've started selecting regions of interest yet for your lab, but you're going to realize that, hey, this isn't the most exciting thing in the world to do, right? Pick those ROIs. The last thing you want to do is going to want to pick more of them, right? But to get a good estimate for your classification accuracy, you really need to do that. Now, the best method to do is the most work, of course, and that's to have a randomly selected data set. Right? So now, how does that work? Well, in a package like Envy, Envy actually implements this. You could have Envy present a single pixel to you and say, which class does this belong to? You say, that's class number 1. All right, here's another pixel. What class does that belong to? Well, that's class number 4, and so on. And what are you doing? Well, you're by hand picking ground truth and setting ground truth for all the data points in the scene. Hopefully not all the data points in the scene, some subset, right? But when you think about that, you want to develop good statistics. So you're talking, you want 50 to 100 points per class. That's 500 answers you just had to give to this program, and that's painful. Okay, that's very painful, right? But it's really the best accuracy that you can really define. Now, it should be the lowest, right? And here's why. And you know, in this example here again, wow, look at this one class. Class 2 went from 86 to 74 to 30. Right? That's it's probably an exaggeration, right? But it's trying to get the point across here. All right. So what might have happened there? Well, if you think about, let me bring up Envy for a second. We'll bring up that Rochester scene. Okay, let's we're actually in a pretty good space right. All right, so here's the river. That's the Genesee River. What's that? Oh no, wait, that's 390. that's a highway. Where'd the river go? Here's the river. Thank you. All right, there, that's the river. All right, now, remember you have 30 meter pixels. Right, so every pixel's 30 meters across. The Genesee River, if you went out on East River Road here, how wide is it? Maybe 30 meters, right? Maybe,
Yeah, I don't think
you know, it's maybe 100 feet across, 150 feet across. That's like a good estimate, but it's not all that big compared to a 30 meter pixel. So if I asked you, that pixel right there, what is that? Well, you'd look at it, you'd say, oh boy, it's not really green, it's not really brown. What is it really? What do you think it probably is? It's probably a mixture of the side of the riverbank, or the road that's next to it, and the river water itself. Right? That's what we always refer to as a mixed pixel, right? A pixel that contains 2 actual materials. And almost everything in the world is a mixed pixel, right? A pixel that falls right here is half screen and half black curtain, right? Look around and tell me where you're not going to get a mixed pixel. Well, most pixels are going to be mixed. So what would you assign that to? Well, you'd have to make a decision. You'd have to make that call. But that pixel is actually going to get assigned to something by the classifier. Right? It's going to assign it to probably either soil or river water, depending on if you pick those classes. And those are going to be the tough ones, right? Those are going to be the ones where you're going to make a lot of mistakes. Are those pixels going to be in your training samples?
Depends if you did the right or wrong thing.
No, for your training. When you were training your classifier. Right, you'd probably avoid those pixels. You try to pick the purest pixels that you could find to do your training with. So if you use those to evaluate your classification accuracy, you're never going to have mixed pixels in there. Here, you're going to have mixed pixels, because if you just select pixels randomly from a scene, you're going to certainly 5 pixels that are on borders between two classes, and you're going to have to make a decision one way or the other. Okay, just like a classifier is going to have to. So if you do use this method, you're going to see a lot lower classification accuracy, but probably more representative of how good your classification actually was. All right, so what do you think is a good classification accuracy? 100% sounds pretty good, right? You know, it's a hard question to answer. It depends on your problem. USGS, when it's making its land cover, what they call land use land cover maps, LULC maps. You could buy products from the U.S. Geological Survey that are 30-meter pixels, Landsat resolution pixels that map, you know, the entire U.S. Yeah, the entire U.S. I don't think they go internationally. But you could buy those products, and how do they make those? Well, they took Landsat type imagery, classified, and produced those products. And what USGS calls a good classification accuracy is 85%. So
On 30-meter pixels.
on 30-meter pixels. That's pretty good, on 30-meter pixels to get 85%.
Depends on the application, right?
Absolutely.
I did land classification, and we would get studies from other countries, and they'd be like, we did such a good job. We were using Lotus, and we were using like 1-meter resolution and doing a better job classifying them. It's all relative.
Yeah. Oh, I mean, it depends on what you're interested in, what your problem is. That's where those risk functions come into play. Right? And so, it's a very nebulous call about what a good classification is. But it really depends on how accurate you need to be for your particular problem. USGS, for providing land cover types, decided 85% is their target. All right, now, if I classified using a Gaussian maximum likelihood classifier, and I classified using a minimum distance to mean classifier, you can imagine I could produce a confusion matrix for each of those. And then I might ask you the question, which classifier did a better job? Minimum distance to mean or Gaussian maximum likelihood? Right? Deep down in your heart, you probably believe Gaussian maximum likelihood did a better job because the math's harder. Right? It has to do a better job. Right? But if you have extremely non-Gaussian distributed classes that you're working with, it probably didn't do all that great of a job. Minimum distance to the mean might have done better. But if what you have is two confusion matrices, what you would need to do is you'd need to compare those to one another and try and come up with a way of saying, hey, this confusion matrix, which is from minimum distance to the mean, is better than this confusion matrix, which is from Gaussian maximum likelihood. Okay, you'd like to be able to say that. All right, now, there is a technique that came out in the early 70s in the statistics literature by a guy named Cognaton, C-O-G-N-A-L-T-O-N. And this guy, if you Google Scholar, Cognaton, you'll see papers from the early 70s through the year 2000, and every paper is about evaluating classification accuracy. It's amazing. I mean, it's just a wealth of literature by this one investigator. So definitely something good to follow through, but what I want to give you here is pretty much the punchline from all of that. Now, there is a concept in stats. He didn't come up with this concept, he just came up with it as a way of looking at remote sensing data, called the Kappa coefficient. And it's really devised to look at these contingency tables and statistics and figure out if one data set or one experiment was different than another experiment. And that's what we're doing here. If we apply one classifier and another classifier, that's the equivalent of doing two different experiments. And we want to see if one experiment produced a better result than the other experiment. Now, the way you go ahead and you compute this Kappa coefficient is this equation 976 right here. And what is it trying to do? Well, it's trying to look at two different probabilities. One of those probabilities is the probability that if you just randomly assigned every pixel in the scene to a class, how well would you do? Right? If I had 5 classes in my scene, and that's really what I had in my scene, and I took pixels and randomly assigned those to a class, you'd expect to do how well? What's that? Well, if I can assign it to one of 5 classes,
Oh, well.
right? It's probably less than 50,
Yeah,
20% or so. But it's really going to also depend on how many pixels in the scene are of a particular class type, right? So if there's only 10 pixels in the scene that are in class 1, there's 100,000 pixels that are in class 2, I'm probably not going to have 20% each of those classes for chance. So this P sub C here is a measure of the probability of, by chance, assigning pixels correct. This P sub O is what they call the observed probability, and that's really an average of the probability along that major diagonal. Okay, so this is how well did I do? How well did I put pixels in the right class? That's what the major diagonal elements of the confusion matrix say. Right? How many pixels were in class 1 that I assigned to class 1? And what this attempts to do is it attempts to remove the probability of a chance assignment to the correct class. Right? So what we're doing is we're taking away the probability of a chance assignment to the correct class from the actual assignment to the correct class. Because if there's a high probability that by chance I could put it in the correct class, well, that should reduce, the quality that I'm looking at in that classification. All right, so the Kappa coefficient is P sub O minus P sub C over 1 minus P sub C. If you go back to Tomlinson's earliest paper, he'll go through the derivation of this equation. But this is the punchline, and Kappa coefficient. And P sub O, if you look right here, it's the sum of the major diagonal elements of the confusion matrix. So C sub I for I equals 1 to K, where K is the number of classes in the scene. So this is the number of pixels. Right? This is my I. Remember I said a contingency table can contain one of 2 things. It can contain the number of things in a class or the percentage. Right? This is the number, not the percentage. And I don't think that's very clear as you read through the text. So make a note of that these values should be the number. And the reason that is this n is the total number of pixels that we're looking at across all classes. Right? So if let's say I'm doing the first case where I'm using dependent data and I'm using all my training samples, n is the total number of pixels in all the regions of interest that I selected for all classes. C sub I is the entry in the confusion matrix. So what is this? This is the average number of pixels that I got correct across the scene. So if I have 4,000 pixels and my major diagonal, the trace of that matrix added up to 3,500, that meant I got 3,500 out of 4,000 correct.
So that's the total number of pixels in the scene?
Total number of pixels that I'm evaluating in my confusion matrix.
So just the diagonal pixels?
No.
So it's not relative to the number of pixels of a particular class?
No. No. So let's go, actually, the example here is in percentages, but put together the same example here in number of pixels. Pull this up real quick.
You need to have the entire scene classified to make these matrices though, right?
No. In fact, you usually make these matrices before you run your classifier.
Oh, so you mean just based on your training?
Based on training data, yeah. All right, so here, let's see, do I have the right one? Yes. No. No, neither one of these is the right one. All right. So, but I can use these as an example. All right, so let's look at this confusion matrix right here. I have 5 classes. So let's assume they were the same as these. So pasture, deciduous trees, coniferous trees, water, and barren. And then, so the truth rows over here, what I would do if I added these pixels together, this would be the total number 251, total number of pasture pixels that were in my evaluation set. In my training data, my independent data, my randomly selected data, you name it. Whatever way you wanted to get those, I had 251 total. I had 54 total deciduous tree pixels, 34 total coniferous tree pixels, and so on. Okay? So these sets of marginals over here that you compute based on a confusion matrix that has number of pixels in it, not percentages like is shown over here, right, but actual numbers of pixels. These are the total number of pixels that are in my training set. So if I add these together, I get 413. And so I have 413 total pixels. Now, if I wanted to go ahead and compute that P sub O,
It's up there.
is it?
Yeah, you just got rid of it. See, it's on the top of the screen. Cell E19, C20.
Wow, I honestly don't.
Above the select on the BF.
It's right.
Oh, huh. Okay, there it is. Thank you. All right. So if I highlight that, what did I do here? Well, I summed up B19, C20, B21, B22, and F23. I summed up those values, the major diagonal, and I divided by 413. So it's just, this is the total number of pixels that were classified correctly, divided by the total number of pixels in the evaluation set.
So there is no way of getting PO from that particular confusion matrix just
From-
as it is.
From these, with the percentages? No. Unless you know the numbers of pixels.
Right.
So that's why I was saying the confusion matrix needs to be expressed in numbers of pixels. All right, now, the next term, P sub C, right, is this product. Now, think about what we were just looking at. We were just looking at the major diagonal terms. So we were only concerned with the numbers of pixels that were right. Okay? What the Kappa coefficient brings into play is the number of pixels that were incorrectly classified also. So any of the methods that I told you so far really didn't look at the number of incorrect classifications. So what does this terminology mean? C sub I t and C sub t I. Right? Well, C sub I t, if you look at the value here, is for class I, right? And we're talking row column format here. So this is row, this is column. Right? So for class I, what I'm going to do is I'm going to add the values across the row. Right? So these are the contingencies for the rows. And so if we go back to the example over here, it's the sum across the rows. So it's the total number of pixels that were in the evaluation set for each of the classes. The C sub ti are the sums down the columns. Right? So they're the other contingencies, they're the column contingencies. Or, I'm sorry, marginals, column marginals. So these won't necessarily add up to the numbers of pixels in the classes because they're the number of pixels that the classifier assigns to a particular class, not that are really in that class. Okay. So these values will be different, as you can see. All right, now P sub C is the summation of the product of those marginals. Right, so if I highlight that, right, so essentially what do I have? Well, I take 251 and multiply it by 201. Then I take 54, multiply it by 80. And I take 34 and multiply it by 37, and so on. So, think about what that's going to come out to be. Right? If everything was classified correctly, what would I do? What would I have here? So I'd have just the sum of the squares and the number of pixels. and I would divide that by the square of the number of pixels. If I have anything less than the number of pixels classified correctly, I'll get a number lower than that. All right, so that's my probability of assigning due to random chance. All right, so if we go back a slide here, now we got everything we need to compute this Kappa coefficient. All right, so to put into words what the Kappa coefficient means, I looked up a couple different texts and looked at the definitions that were out there, and I think these two really hit it on the nose. Let me hop out. So referring to this bottom example right here, to this contingency matrix, the Kappa coefficient represents the proportion of agreement obtained after removing the proportion of agreement that could be expected to occur by chance. Right? So it is a classification accuracy. That Kappa coefficient is a classification accuracy, removing from the accuracy what was contributed to that accuracy just by pure chance. So if we look at the average accuracy for this particular confusion matrix, it was 84.8%. That was just the average of the major diagonal elements. And so I'm sorry. That was the weighted average of those elements. Right? The overall accuracy was the straight average of those elements. Okay. So the weighted accuracy was 84%. The average accuracy was 81%. The Kappa coefficient came out to be 70%, much lower. And what does that say? Well, it says that with 5 classes, there is some significant chance that you're going to get it right just by guessing. Right? We want to remove that from the equation. So when people report a Kappa coefficient, that Kappa coefficient can be interpreted as a percentage classification accuracy with chance removed. All right, now that's valuable, right? Because I could go ahead and I could assume this came from a Gaussian maximum likelihood classifier. I can go apply minimum distance and mean to the same data set, compute another Kappa coefficient, and I can get two very accurate, very conservative classification accuracies out of here. And now the question would be, are they different? Okay. Now I didn't do this computation because I knew I'd get it wrong, typing it into Excel. But here's how we do it.
One question, Barb.
Yep.
When you have over there overall accuracy and average accuracy,
Yes.
so the overall accuracy is the same as the PO. Right?
Yes. It's just the average of the trace. Okay, so I took
So
trace
the
of that
sum
main-
of the diagonal over the entire
Yep.
data set.
Exactly.
Well, yeah, the entire number.
That number of points in that data set. Yeah, so those should be the same. Yep.
And then the average accuracy is what? Divided by each.
Divided by the total number of pixels in each of those classes. So
So those are
195
the
divided by
percentages.
251, 45 divided by 54, 22 divided by 34, 68 divided by 69, 5 divided by 5, and then the average of those.
So it's averaging the percentages that we had.
Yes. And you'll see those reported. So I just wanted to put out all the things that I've seen reported. All right, so the question becomes, are two classification accuracies different from one another? And you've done those kind of tests in stats before, where you did the z-test to see if two populations' means are the same. I mean, that's essentially the same computation that we're going to do here. So one of the things we need to come up with is the variance for the Kappa coefficient, right? And this goes back to Congleton's original paper. That's the variance of the Kappa coefficient. I'm going to leave that to you to derive. Right, we'll probably have that on the next test. No, I'm kidding. I will never ask that question. If that question appears on the test, you can assume it's a joke and not answer it. Good comp exam question. No. I wouldn't do it there either. I don't know how you get there. All right, but this is the final equation. That's the variance of the Kappa coefficient. Right. If you look in here, all the terms are P observed, P by chance. and there's this A1 and A2 term that show up, which are, if you look at this, you got a double summation over all the elements in the contingency matrix multiplied by divided by n cubed. I don't know where that comes from. Right? I'm just gonna take this one on faith. All right, so, but if you can come up with that value, now what do you have? Well, you have a measure of the spread on your kappa coefficient, right? So the kappa coefficient follows some distribution. In this case, it's a normal distribution. So we can go ahead and we can do a z-test to figure out if two kappa coefficients are significantly different than one another. Right? So for instance, if you wanted to form a 95% confidence interval, you can compute that variance, take square root, get standard deviation, multiply that by 1.96, and that would contain, that range would contain 95%, or would form a 95% confidence interval around that kappa. So kappa could be as small as what you compute kappa to be, minus 1.96 times the standard deviation. It could be as large as the kappa you compute plus 1.96 times the kappa, standard deviation of the kappa coefficient. So that would just give you a range. Now ideally, you don't want those ranges for two kappa coefficients. If they don't overlap, then you could say they're significantly different to 95% confidence. If they do overlap, well then you got to make that decision. Right? And that's where a typical z-test would come into play. Our null hypothesis would be that the two kappa coefficients from two different classification techniques were equal, all right, or that the difference between them was 0, and that would be your null. And then your z-score for this particular case is the difference between the two kappa coefficients divided by the square root of the sum of the squares of the standard deviations. So a typical z-score for a two population z-test. So you go ahead and compute z. If z is greater than 1.96, in other words, for an alpha of 0.05, 95% confidence in your answer here, is greater than 1.96, then you can reject the null hypothesis and say that one of the classifiers is better than the other. One with a higher kappa would be better than the other. If you fail to reject the null, in this case, you could say that there's no difference between the two classifiers. So if z was less than 1.96, you'd be in the case where you could say those two classifiers are the same. Didn't make any difference. So if what you're trying to do is say, hey, is my classifier better than Gaussian maximum likelihood? So you came up with a new classification scheme. You can go ahead and compute the kappa coefficient for each based on a set of training data and determine that. Right? So and you'll see a whole bunch of papers out there where somebody says my classifier is better than this classifier because GML gave me a 92% classification accuracy, and my new classifier gave a 92.5% classification accuracy, so mine's better. You probably saw that, right? In your sort of analysis. If you went ahead and you did this comparison of kappa itself, you could determine if that is true statistically. Make sense? All right. I don't remember if Monica asked you to compute kappas in the lab or not. Envy does put those values out for you. So, oh, okay. That was dumb. So let's just do that really quickly. If you go in to Envy, you open up one of your images, view classification. Alright, so there's our image. Put some ROIs on there. Story. Alright, got some ROIs. We could do a Gaussian maximum likelihood like we did the other day. Use all the bands, use all that. We're going to assign probability, prior probabilities to be the same. Put the output memory. Let that run. Alright, so we get our class map. Display that. And so there's the classification we got the other day. Alright, so now that you're done with that, you want to say, how good did I do? Right? So under classification, there's a post-classification pull-out menu here. And one of the things that you could do is confusion matrices. Right? And you could base it based on your regions of interest, or if you have a ground truth image, in other words, a map you want to compare it to, you can use that map to do that. So we'll do it based on ground truth. Let's see, classification input file, that's your class map that you just produced. And you can add combinations of regions of interest down here at the bottom that you want to compare. So, ooh, that wasn't effective. All right, so what do I have down here? Well, I want to compare bay water in my regions of interest to bay water in my map, river water to river water, urban to urban, and so on. I have all 5 classes in there. Okay, you can go ahead and you can compute that. You can have your output confusion matrix in pixels or percentage. Okay, so let's do both. Take a look. And report accuracy assessment, sure. All right, so there's the answers. All right, so here's my confusion matrix. Golf course grass compared to golf course grass, how did I do? Yeah, pretty good. That's 100%. Or is it?
No, you
Did I miss 2?
No. That's good.
Yeah, that's 100%. This is the truth. So I assigned 155 golf course grass pixels to golf course grass. In the case of Bear Field, 2 of them got assigned to golf course grass. Let's see, where else? Wow. That's the only mistake. Yeah.
But this is
It's not
the
bad.
first confusion matrix you're talking about. This is the dependent data.
Yeah.
Okay.
All right, so how well did I do? Well, I got 99.8% for my Kappa, right? And I got 99.86% for overall accuracy. So 1,423 pixels right out of 1,425. Yeah, that's why I'm teaching up there. That was pure luck. That's the first time I ever actually looked at this. I don't know how that happened. But you can see that the Kappa coefficient and this are in fairly close agreement, so you should get a really good feeling about that. If I went ahead and I did another classification scheme, let's say we did minimum distance to the mean, I can come up with another Kappa coefficient, and we can see how those two compared with one another. What's missing here? That variance isn't here. And it's nowhere in this stats list. So if you want to compare 2 to each other, you have to take that offline and do it on your own. I'm very surprised that it's not in here, but it's not. Man, look at that. That's the percentages. Okay. Any questions on how you compare these things?
So you showed us a formula for the variances. So will we have?
That's the variance.
So we had all the elements of it.
We have them all except for this A1 and A2 term, but they're just based on the contingency table values. And so a little MATLAB function can be all set. No questions? Everybody good? All right, so that's supervised classification. That's how we look at the classification and say how well did we do. So now the next thing I want to take a quick look at, and it shouldn't take very long, is the concept of what's called unsupervised classification. So I'm going to hop out to some notes here. Let's see. So again, these are the notes that are in the image processing class. So in session 17 of that image processing class, there's unsupervised classification. Now, this whole concept of understanding 2 things, understanding how your data is distributed and understanding that you know how many land cover types are in your scene. Like, those are two very difficult assumptions to really justify yourself. Multivariate normality, maybe you can believe that. If you look at enough histograms and they're unimodal, you can probably convince yourself that you're doing a pretty good job of that. But I would be willing to bet that if you plotted one band's histogram for any training data that you picked, you're probably not going to see multimodal data. After a while, maybe you get used to picking things and you become more critical, and you might start to see it. But in your first go around here, I can almost guarantee that you see multimodal data. Right, so you're violating that assumption right there. You're also making a really big leap when you say, all right, here I have this scene of the RIT campus, the one you have for your lab. How many cover types are there? How many land cover types are there? So you look at that scene, and you can spend a very long time, and you could probably come up with 30, 40, 50, 100, some very large number of cover types. And then you take a step back and you say, wow, I got digital image math homework to do, I got to do optics, I got to pick 100 training samples for these 100 classes. Right? This lab's only worth 5 points out of the grade. Right? So you probably make that, you'll assign a risk function, right, to your grade, and you'll say, you know what, I'm going to pick 10, right, because I only see 10. And you'll convince yourself you only see 10, right? And you'll go through and you'll pick those. That's a very hard thing to do, right? And you'll always be wrong. You're always going to pick less than there's actually in the scene. So unsupervised classification helps you get past that. Unsupervised classification just looks at the data. It looks at the statistics of the data in the scene, and it says, you know what, I'm going to pick classes for you. I'm going to pick them based on their statistical separation from one another. How far apart are they from one another? And let me pick as many as I can find. So that's what unsupervised classification sets out to do. All right. All right, so we looked at distances, right? We looked at Euclidean distance. We all know how to compute Euclidean distance. There's something called an L1 norm, which is just another measure of distance. It's the sum of the absolute values between all the pairs, as opposed to the squares. Why do people do L1 norms? This is a lot quicker to compute than this one. Squares and standard deviations, again, are expensive. Absolute values aren't. Right? So for computational purposes, the L1 norm is often used as a distance measure. And if I looked at this set of data, right, I could probably look at this data in many different ways. So what am I looking at here? I have, let's say, band 1 versus band 2, right? And I have, 12 data points here. If you looked at that data set, you could probably draw these ovals I just drew and say, those are 3 different classes. Or you can take those same data and draw those 5 ovals and say those are the classes. Or you might draw those 3 and say those are the classes. Right? But all those data are laid out identical. These 3 layouts are identical to one another. But you can go in and if you were just looking at this data, you could probably go in and circle and say, hey, these things belong together. Okay? So which one of those is the best? Which one of those is the best set of classes? Well, that's what unsupervised classification attempts to do, is tries to figure out which one of those is the best one. All right, now, the way that it does that is it'll look at the clusters that you assign, right? If this is cluster 1, this is cluster 2, and this is cluster 3, the how good comes into play by looking at distance. Right. So if this is a cluster, where's its mean? Well, its mean's right there in the middle, right? And as a measure of how good this cluster is, I can compute how far away each point in that cluster is away from that, and sum it up. Right? I want nice tight clusters in space. So are these 3 better than these 5? Well, I can go ahead and I can compute the sums of all those distances from all the points inside of a cluster, add them together, and the smallest one should represent the best set.
But aren't you just looking at 2 two bands right there?
In this case, just two bands.
So if you're looking at more bands.
Your distances are just in higher order space. In this case, it's just in two space. All right, so typically what you will do is that quality metrics, we'll use the sum of squared errors, where we look at how far away each point in each cluster is away from its mean, and we add those up. All right, and when the sum of squared errors gets to be the smallest, we have our best set. All right, so let's just look at an example how that might work. All right, there's an algorithm out there. There's really two algorithms out there that are used for unsupervised classification very frequently. One's called isodata, and this was developed back in the early 1970s at the Laboratory for Applied Remote Sensing at Purdue University. And you know, it's out there as a standard that people compare to all the time. And it's very similar to a technique called k-means, right? Classification. So let me go through isodata and you can get an idea how these things work. All right, so what do? Well, you have this optimization going on where you have seed points that you want to classify in multivariate space. Right, so these are the points in your scene. All right, so initialize the optimization with seed points in multivariate space as candidate cluster means. All right, so I'm going to look at my scene and I'm going to take C points out of my scene and I'm going to say those are my means for my clusters. Right, now, how do you do that? Well, let's say we have a 7-band sensor, so we have 7-dimensional space. I could generate C random 7-element vectors. Right? So I could generate, let's say I wanted to have 10 classes in my scene. I could generate 10 7-element vectors and put them out there in 7 space and say those are the means of my clusters. All right? Or I can go through and pick 10 random pixels from my scene and say those are means of my clusters. I like the second one better because at least you know you're going to have one member in a cluster, right? The pixel that you picked. It's going to be closest to itself. And so that one's always going to be assigned. If I just pick 10 random values in 7 space, chances are I'm going to have 4 or 5 of those that never have a pixel that's close to it. It's just somewhere sitting off in the end space. So the original isodata paper suggested that you randomly pick these points. I'm going to strongly encourage you never to do that, and that you should pick random points out of your scene as initial cluster points. All right, so no two candidate means can be the same. All right, so you want to make sure you have C unique points. All right, and as general, they should be distributed over the scene. You don't want them all clustered in one area. You don't want to pick 10 grass pixels randomly. Now you're randomly picking these things, so chances are you're going to get duplicates. So if you think there's 10 classes in the scene, maybe you should pick 20. And then you know, good chance that you'll get all 10. Maybe you want to pick 50. There's no good rule of thumb, but you typically want to get a much larger set of means that you think there might actually be classes in your scene. Now, what do? Every pixel, or some subsampling of pixels, are assigned to the cluster based on which cluster mean they're closest to. So now you go through and you had C cluster means. You look at all the pixels in your scene and you assign them to the cluster mean they're closest to. Okay? Now, once you have those clusters, pixels assigned to each of the cluster means, you recompute your mean for that cluster. So that's going to shift your mean around. All right? And then you start the whole process over again. You assign all the pixels in a scene to cluster means they're closest to. And you recompute the cluster means. And you do it again. And you keep on doing it until your cluster means no longer change. Right? So you keep iterating through this algorithm until your cluster means don't change anymore. What does that mean? It may none of the pixels are changing class membership anymore. So just pictorially, you know, you might look at it this way. If I had these pixels in 2 space, band 1, band 2, and I randomly picked 2 means, right? This is what I told you not to do. I just randomly picked 2 means, and they happen to come out here and here. Well, I can assign these pixels to the mean that they're closest to. So in this particular case, these two, this one and this one, got assigned to this mean, and the rest of them got assigned to this mean, just because of distance. All right. Now, once I make those assignments, I recompute the means. Now you can see the means are in the middle of those clusters. And I could then assign pixels to the closest one. So you can see that I pulled this one away from this mean and assigned it to this mean, which I've read over here. Then I can recompute the means, and shift a little bit, do the assignment again, and some other ones jump. And I can keep doing that until none of them jump membership. Okay, you can see between this iteration and this iteration, none of them changed. They're still all belonging to the same class. So in that case, I would stop my iterations. Another way to do that, because this is very dangerous, when you start having millions of pixels, what are the chances that not a single one of them is going to jump class? That's probably pretty low. So what you could do is you could plot that sum of squared error that we had back a couple slides ago, this sum of squared error, as a function of iteration. And you can see that the sum of squared error went from 77 to 20 to 19 to 16. And if I plotted that, at some point it would level out. And then I know I can stop my iterations. So I could iterate until my sum of squared error doesn't change by more than 0.5%. Set some threshold value. Now, if you have, in this case we picked two classes, but if you look at this data carefully, what would you say? Do you think there's two or do you think there's three there? To me it looks like three, right? But we only picked two, right? So we're only going to get two. So what these unsupervised classification algorithms allow for, or have options to do, is these three things. You could split a cluster, right? So if we go back here and we look at these two clusters, do you think that point really belongs with these three? Probably not. Do you think this point really belongs with these four? Probably not. So what splitting can do is if a cluster gets too elongated, so in two space that's easy to see, if it gets too ellipsoidal, right, you might take a look and say, hey, is there a point in here where I can split that cluster? And say, you know what, you 3 points, you have this mean, this point over here, you have another mean. And then look at this one and say, I can split that cluster too because it's too elongated. Right? And you would look at something like the eccentricity of the ellipse that formed in n space, or the hyperellipsoid in n space, and be able to figure out whether that's true. You can look at the variance in your data set, and if the variance in one of the axes is too big compared to the other, you might consider splitting it. You can plot a histogram, right? And if you see a multimodal histogram when you project onto one of these axes, you might think of splitting it. Probably in next quarter in image processing, you'll see a method called Otsu's method, which plots a histogram and looks for values in the histogram and splits based on that. You can imagine if you can project this onto the L1 axis or the L2 axis, you can use something like that to split them apart. There's all different kinds of splitting algorithms that are out there. But you want to allow your algorithm to split, okay, to make more classes than you might have started with, because it can make that decision based on data, as opposed to you guessing. Right? You also want to be able to delete clusters. If a cluster winds up with 1 pixel in it, right, chances are that's probably not real. It might be a dead pixel on your sensor. It might be a single car, in the scene that, in a forest. But most times, if the clusters are too small, you can tend to just delete the cluster, just get rid of it, and allow that pixel to go to another cluster. Right? Rule of thumb is 10 endpoints in n-dimensional space. So if I have 7-dimensional space, if I have less than 70 pixels in a cluster, you would delete it. Again, rule of thumb, there's no statistics backing that up. I can't give you a good reason, but if you look through everybody's literature that they had out there, people usually use that as a pretty good guide. Merger If two clusters are just sitting right on top of one another, it might be the same cluster. They might actually fall together. But because you said there was 7 clusters, and there was really only 6, 2 of them were forced to form real close to one another. If they are too close, and you can compute that, right? You could do a multivariate z-test and compute, is this mean with this covariance matrix different from this mean with this covariance matrix? If to 95% confidence you can't say that's true, merge the 2 clusters. Right? So you can merge based on simple z-test in n-dimensional space. You can delete based on number of pixels in a class. And you can split based on how spread the data is. So by being able to do those 3 things, you can allow your algorithm to overcome what might have been a bad guess at the number of classes in the beginning. All right, so let's oh, goddamn, keep closing in. All right, let's try an unsupervised classification here. Look at how that. All right, so we'll take that same scene, and let's go ahead under classification and choose unsupervised. You can see there's ISO data as a choice there. Ask for your input data set, and we'll use all the bands. All right, number of classes, minimum 5, maximum of 10. Those are just the values that they chose to put in there as default. All right, so minimum of 5, sure. Let's bump the maximum of 20. Maximum number of iterations, 1. Right? I don't know why that's the default. All right, so let's bump that up. Let's do 20 iterations. Change threshold. This is how much, if I look at that sum of squared errors, how much can it change to say I need to do another iteration. So if the change is greater than, in this case, 5%, it'll continue on to do another iteration. Right? You can lower that number if you want to tighten that up a little bit. Minimum number of pixels in a class, that's for deletion. Right? In this case, they have 1. That's fine. Maximum class standard deviation, 1. What does that mean? Well, that's the standard deviation that it'll allow a class to have before it splits it. All right? If it's larger than that, it'll split it. So we'll leave that as a default. Minimum class distance, 5. That's how close 2 classes could be before they merged them, right? What's the very unsettling part of all this? What the heck is 5? Right? I mean, this is a distance in 6 space. I don't know what that means. I don't have a good feeling for that. I would really much rather this be based on a z-score. Right? But the only thing they give us is a number here. Okay, so let's just go ahead and leave that. Maximum numbers to merge. So at any one time, how many clusters can merge together? And in this case, it's 2. That kind of makes sense. Right? But you can up that if you want to let 3 come together at one time. All right, so let's put our output to memory and let this thing run. What do we say? 20 was the max. Let's see how many we get. 1 iteration, 2 iterations, 3 iterations, 4.
Are the iterations picking a new set of random start points?
No. The means,
They're recomputing
the means get recomputed each
Okay.
time. All right, so it went somewhere around 10 maybe. I don't think it went up to 20. All right, and here's our class map. So if we display that. Ooh. All right, so there's your class map, right? Based on the statistics of the data. So, nice river, look at that bay, right? These things came out nice. You can start to see street lines in downtown. You can see all the streets in the suburbs. Probably people's driveways, minor roadways. The grass at the airport, much different than everywhere else. There's those bare fields, right? They showed up really nicely. This does a really, really nice job. At first it might look at, wow, you know, that didn't do a great job. But at this point you can go in and you can start combining some of these things together that are, you know, in your knowledge, the same thing on the ground. But this did a statistical separation of these as best as you can do. Now, I don't know how to find out how many it picked. Let's see. That's not right. It did find 20. Right, so that's what we said the max was. So we could have gotten more. If we said 25, it probably would have found more than 20. Right, so when you run an unclassified or an unsupervised classifier and you don't know what that number is, if you get the maximum number that you asked for, then you know nothing was merged, nothing was deleted. So you probably have to have a pretty good feeling that you didn't pick enough. And you think there's more than 20 things in Rochester? Right, in all the surrounding area? The answer's probably yeah. But if you look at that compared to that map that we generated the other day based on just selecting 5 classes, you can honestly, if you look at this close enough, you see that you're actually doing a much better job. Now, one of the things that I think you're doing in your lab is you're going to run an unsupervised classification, then you're going to use this to help yourself pick training samples to do supervised classifications after the fact. So you get to combine these two techniques together. Great. Questions?
So do you not have those 3 options, the deletion, the splitting, and the merging in k-means?
K-means does not have those options. Right, so k-means just assigns to the closest class, and it gets as many classes as you ask. So there's never combining, there's never splitting, there's never deletion, and it's just based on, k-means is based on just simple Euclidean distance.
So it's basically the first part of ISO.
Exactly.
Okay. But when you don't even know what the numbers mean for the merge and stuff, it's like what?
Exactly.
Why even do
So
it?
my recommendation would be, if you're ever going to do unsupervised classification for real, is to write your own algorithm where you really understand what those statistics are giving. I mean, these packages are great, they make it easy, but it's sort of a black box that you don't know what's going on inside. Now, that being said, there are manuals, right, that you can read and they probably explain what that is. But that's not fun, right? Questions? All right. So what I want to do next time is I'd like to take a look at the concept of separability. Right. So if I have a scene and I want to figure out how many classes there are in the scene, you can do something like this. If I have a scene and I want to figure out, can I tell 2 things apart from one another, right? So I'm really interested in distinguishing maple trees from oak trees, and that's my goal. With my data set, with my 6-band Landsat data set, can I do that? So that's what I want to answer. I'm trying to answer that question. I'm trying to figure out, with the data that I have, can I solve a problem? And with the data that I have, if my goal is to separate oak trees from maple trees, and I have 6 bands, are there 2 bands that would do it for me? Right? Can I figure out some subset of all my data that I can use to solve my particular problem? Right? So that's the concept I want to look at next time is how you do what's called optimum band selection. So if you go and you design a hyperspectral system that has 2,048 bands in it, and you put that up on an aircraft platform, and your goal is to figure out can I distinguish concrete from asphalt? or something, you know, a task like that. And you have very limited bandwidth down from your aircraft to the ground, right? Passing 2,048 bands down from an aircraft to the ground in real time is a very difficult thing to be able to do even today. Is there 7 bands out of that set that would solve my problem? And if so, which 7 bands are they? Right? So that's what I want to look at next time, is this concept of separability and optimum band selection.
Can you do like spectral PCA, or do you kind of ruin your spectral data?
Oh, no. We're going to do spectral PCA next time too. So what, you know, after we look at separability, which will kind of finish up this concept of distance, we're going to look at what can we do to this data set to actually do a better job. 6 bands are 6 bands. 2,048 bands, you know you have a lot more data than you have information.
But it won't ruin the shape of your spectral.
Oh, it'll totally change it.
Okay.
Yeah, it'll absolutely change it because you'll be in a new data space. Yeah, so your spectral signatures will be different, but they're still spectral signatures. They're just not physical reflectances anymore.
And you'll find that sun and shadow ones are still just changes of magnitude, that they would have theoretically the same shape if you're projecting them on the same magnitude.
I don't think so.
So it kind of gets rid of a lot of the algorithms.
No. Well, wait. Well, why do you say that?
It's like the one that we were talking about, the angle,
Okay.
earlier today.
Yeah.
So to do the things that are the same shape but just different magnitude.
You can still have that same concept in PCA space. I mean, you can still have the concept of brightness. I mean, when you do an eigenvector transformation, your first eigenvector, typically all the coefficients are the same sign. Right? So they're either all positive coefficients or all negative coefficients, which implies that your first eigenvector, and we'll look at this, your first eigenvector is a weighted average. So it's a brightness term. Right? So that brightness stays around. So it is still existent in an eigenvector space. So remember, next time Dave will come in. So if you have any questions about, you know, how the process of picking a project goes and all that, make sure you ask Dave on Thursday. Most of that stuff. Yeah. We can probably all get a little antsy now. Let's start doing something, right? Besides going to class.